Hello, today on the Woken Way we're going to do 3.5, which is modeling with exponential and logarithmic functions. So this is the real life application part, maybe not our real lives, but somebody's real life. So we are going to start by looking at the two typical exponential growth and decay models. One is written as a function and one is just written using a, so they are exactly the same, it just depends on the question. A naught, if you remember from science, is the time at the original amount, so time is 0 at that spot. A, or f of t, is the final amount. K is the constant for growth or decay. If k is greater than 0, then the function represents exponential growth, and if k is less than 0, then it represents exponential decay. So just tying it to what we already know, if A naught is down here and then it goes up, that would represent exponential growth, and if A naught is here, then it's going down, that would represent exponential decay. So we're going to use these two formulas right now, and then we're going to progress to some other ones. So what I want you to remember is they usually give you enough information to first find k, and then the second thing you're going to do is write the model. Okay, so the model just means write the formula or the equation. So the first piece of information you're usually given comes with two amounts, and then you use that to find k, and then you go back to the beginning and start again, but this time you have k so you can write the actual formula. So it's going to feel very repetitive because it's the same thing over and over again. One thing I do want to caution you about is making sure you read your questions really carefully. We talked about using a highlighter, so I'll go ahead and model that for you guys right now. In 1990, the population of Africa was 643 million. By 2000, the population of Africa grew to 813 million. Using the exponential growth model, A equals A naught e to the kt, where t, oh, that's a good one, t is the number of years after 1990. So it's not just the year, it's the number of years after 1990. Find the exponential growth function that models the data. So the first part, what we're going to do is we are going to write the model, or sorry, we're going to find k and then write the model. So we kind of do these two things twice. So I'm going to start with the formula, and it really doesn't matter which one you use. So this is the one, and by the way, this formula will be given to you on your test, so you don't have to memorize it, even though it's pretty easy. It's almost like that PERT one, remember, that we did early in the chapter? Your final amount equals PE to the RT. It actually is the same formula. It's just applied to a new situation because it's talking about exponential growth and decay. So when we start this, let's start with what we know. In 1990, the population of Africa was 643 million. So this is the initial amount. By 2000, so how much time has gone by? 10 years. The population grew to 813 million. So because we only have one unknown, we can solve the equation. So we're just going to plug and chug here. So our variable is in the exponent, so in order to solve it, we're going to have to take a logarithm, so we need to isolate the exponential. So I'm going to take 813 and divide it by 643 and rewrite that as e to the 10k to make it look nicer. Now, how do I undo this base e? I take a natural log of both sides. Tried to combine my L and my N in one. It looks like an H, so don't want to leave it like that. These undo each other. This doesn't undo each other. By the way, we are going to see that this is 10k, so when I solve for k now, I will have to divide out that 10. So I'm going to get k is equals the natural log of 813 over 643 all divided by 10. And what I wanted to say, where I almost tried to say it here, but I meant to say it right here, is that if this number, like let's say this was a 20 inside the logarithm, if it was part of the argument, and this was a 10, you cannot reduce those because they're not common factors, because it's actually the natural log of 20 divided by 10. And since this isn't part of a logarithm, you can't cancel them. So then we're going to plug that into our calculator, and we're going to go 3 decimal places, so it's 0.023. And then, so we just found k, but it wants us to write the formula. So all we're going to do this time is when you write the formula, your final amount, you're going to leave a, and you're going to leave t, because you're wanting to be able to plug into this formula. Your initial amount was still 643, and your k is 0.023, so your equation is a equals 643 e to the 0.023 t. So your formula should have variables left in it, is what my point is. Should not have k left in it though. Okay, so next what we're going to do is apply this formula, and this one says by which year, so by which year, so your answer is going to be a year. It doesn't say in how many years, it says by which year will Africa's population reach 2,000 million, which is 2 billion. Why did they write 2,000 million instead of 2 billion? They're making your life easier because this formula is in terms of millions rather than billions. So same thing. Right? 2,000. What's our initial amount? 643. This is 0.023. And then we don't know t, that's what we're looking for. So we get 2,000 equals 643 e to the 0.023 t. And what you're probably noticing is that maybe that felt a little bit redundant for you, because you're like, hey Vulcan, if we already have the formula, can't we just plug in 2,000 to the amount? Yep, go for it. Okay, so next I'm going to divide that out so I can solve for the t value, which is in an exponent, so I know I'm thinking the only way to undo that exponent right now is a logarithm. I'm going to just draw that in. I did it again. And then these are going to undo each other. So I get 0.023t equals the natural log of 2,000 divided by 643. And then I'm going to divide that out. Don't mind my dogs. Somebody's walking by. Notice I'm not punching anything into the calculator until I've rounded here. And actually, I didn't even punch it in the last one, so I'm going to go ahead and do it for you in this one. This would be the natural log of 2,000 divided by 643, close out your argument, divided by 0.023. So it's going to be in 49.337 years. So we're going to say approximately 49 years. But what does the question ask? We've highlighted it, so we want to make sure we address it. So it says in which year. So what was the initial year? You have to go way back up there. The initial year was 1990. So 1990 plus 49 equals during the year 2039. Okay? So make sure you read your questions, because they're not always like this. Someone just say, in how many years will its population be this? And you can say in 49 years. So it's very important you read those questions. Okay, next we're moving on to our tricky. There will be one like this on the test. This one's only tricky because at first glance it doesn't seem like you have enough information, but in the spirit of creativity and mathematics you can do this problem. So Strontium-90 is a waste product from nuclear reactors. As a consequence of fallout from atmospheric nuclear tests, we all have strontium-90 in our bones. Now, I know you see a number right there, but strontium-90, that 90 has nothing to do with any values that were given. That's just the name of the element. So use the fact that after 28 years, a given amount of strontium-90 will have decayed to half the original amount to find the exponential decay model. So you're like, what the heck? Well, problem solving. What did we do on the last problem? Because we're not sure here. So A naught, K, T. We know we have to find K first. We know that it took 28 years. What we don't know, we feel like we don't know, is any of these, but we're going to be a little creative here. This is the original amount. We know that this is half the original amount. So why is that going to be helpful for us? Because if we start with our formula and we write the final amount in terms of the original amount, because we can, because they told us it was half the original amount, that switches the variable. We still have two unknowns, but watch. I can just divide this out right here. And they're going to cancel because they are common factors on each side. So then I get 1/2 equals e to the 28k. I'm going to take the natural log of both sides. Those cancel out. K equals the natural log of 1/2 divided by 28. Okay, now I'm going to pause just for a second before we finish this problem. Actually, we can plug it into our calculator and we're going to get negative 0.025. I do want to say it is negative because it's decay. So the other one, the population was increasing, so we saw a positive K value. On this particular one, I have this little sticky note here where I shared with some students, if it doesn't give you numbers, like if it doesn't say half what the original amount is, then you can always make numbers up. Look what happens when you go to solve. When you make this 10 and this half of that, it's 5/10, it reduces to 1/2. So look, same exact equation that we get right there. Now be careful because it's not always half. It'll say 70% of the original amount. So if it said 70%, that would be 0.7. If it said 65%, that would be 0.65. So it's just all proportions of the original amount. Okay, so we are still looking for that exponential decay model. And on this particular one, since we don't actually know the initial amount, the best we can do is write it like this. We found K, but we still don't know the original amount. Hopefully they'd give it to us if they wanted us to calculate anything else. Okay, suppose that the nuclear accident occurs and releases 60 grams of strontium-90 into the atmosphere. How long will it take? So how long will it take? How many years to decay to a level of 10 grams? So using our same model, so it's starting at 60. Remember, it's decaying, so the number should go down. So that's sometimes tricky. So your final amount, which is A, won't always be the biggest number. In fact, if it's decay, it shouldn't be the biggest number because that wouldn't make sense. So here we go again. We're just solving. I actually wrote A when I meant to write 10. Let me take care of that real quick. And then divide out the 60 because I'm trying to isolate the exponential. So I get 1/6. Take the natural log of both sides. So T equals the natural log of 1/6 divided by 0.025. And when I plug that in, it's negative, right? I forgot my negative. Don't forget your negative. Which now we can do natural log of 1 divided by 6. Close that argument. Divided by negative 0.025 is 71.6. 3670 years. Okay, alrighty. The next one I think is a little bit easier. It's just working backwards. You're given the formula and you have to interpret the values that are in the formula. So we have this exponential growth model right here, and it describes the population of the United States T years after 1970. What was the population of the US in 1970? So that's when T equals 0. That's what you have to realize. So you just plug into your formula. Zero times that is 0. E to the 0 power is just 1. The whole thing is 1. So I have 203 times 1, which is 203, which you can see right in the formula right there. So the population is 203 million. We're going to make sure we put our unit on it. And you can see it's also right there. That's because in our formula, A naught is the initial amount, and that, if you look back up here at the beginning, A naught represents your initial amount. So you didn't even have to do all that work. You could have just taken it straight from the equation. By what percentage is the population increasing each year? So that's your value of K, that's your rate. It does ask for a percentage, so I'm going to convert that to 1.1%. So that's the population growth rate. So I'm just going to highlight percentage there, that's K. When will the population be 300 million? So we have our formula, we're just going to plug in. See, this is the part that gets so repetitive because we've already done it 1, 2, 3, 4 times. This is our 5th time of setting this up. Yeah. The same number of times I've made that mistake. So T is the natural log of 300 divided by 203. And then because there's that 0.011 with the T, we got to divide it out. So we get T is approximately 35.507 years. But it says when, so it's not saying how long, it's saying when. So we have to go ahead and figure out what was the initial year, and I have it highlighted, T years after 1970. So 1970 plus our 35.507 years. We're still in this year right here. I mean, like, it hasn't made it up to the 36th year. So we're going to say during the year 2005. So it's probably like what? It's a little bit past half, so we're somewhere in July because that's the 7th month, but we don't need to be that specific. Okay? All right, let's go ahead and flip it over. The next one is our logistical growth. So this is a new formula. It's not the same one we just had. And this one talks about the number of people who become ill with the flu T weeks after its initial outbreak in a town of 30,000 inhabitants. So this one is now switching to weeks, and we have 30,000 inhabitants. How many people became ill with the flu when the epidemic began? Well, our formula doesn't have an A naught, so we're going to use the fact that we know it's going to be F of 0 because T is going to equal to 0 right when that flu began. And you're going to make sure you do your math properly here, so don't go super fast. Make sure you just be diligent. We've talked about that before. 1 plus 20e, negative 1.5 times 0 is 0, which is 30,000 divided by 1 plus 20 times 1, which is 30,000 over 21. And then you're going to plug it into your calculator. we get, it says how many people. So on this particular one, rounding wise, I'm going to round up to 1429 because you can't have 0.57 of a person. Okay, so we're going to say approximately 1,429. And then this question's kind of trickiness, saying what is the limiting size of the function that the population becomes ill. So like I can plug in 1 billion for t, and this might get bigger and bigger. I can plug in a negative number and then see it get bigger and bigger. So what's the limiting size? What is the maximum number of people that can become ill? It's 30,000 because that's how many people are in the city. Okay, we're going to move on to Newton's law of cooling next. T represents the temperature of the heated object. It's kind of like the final temperature. C is the constant temperature of the surrounding medium. So if you're in a freezer, that's colder than normal, and if you're in the desert, that's hotter than normal. T naught is your initial temperature, and then we have that constant temperature again. The temperature at which it's cooling is K, and then T is time. Okay, so let's use this Newton's law of cooling on example 5. An object is heated to 100 degrees Celsius. It is left to cool in a room that has a temperature of 30 degrees Celsius. After 5 minutes, the temperature has decreased to 80 degrees Celsius. Use Newton's law of cooling to find a model for the temperature of the object T after T minutes. So for this particular one right here, we have a new formula, so I'm going to draw it really big because I have 1, 2, 3, 4, 5 unknowns. So I have the final temperature, the constant temperature, so the temperature of the surrounding room, the initial temperatures, the rate at which it's cooling, and the time. So if I set this up, an object is heated to 100 degrees Celsius. So it starts out at 100 degrees, and then it is left in a room that is a temperature of 30 degrees. After 5 minutes, it is, what does it say? After 5 minutes, the temperature is cooled to 80 degrees. So that's its final, which is a little annoying again, but because it's cooling down, the final temperature should be less than the initial temperature. So if this is our starting formula, then we're just going to plug into it. I don't know why I'm putting the degree symbols. You don't have to, but I'm going to be consistent, at least in this step, and then I'll probably stop writing them. And T is 5. Alrighty, and then from there, we're going to do some math. We have 80 equals 30 plus 70 e to the 5k. I'm trying to solve for k so I can write that formula, so I'm going to subtract 30. And then I'm going to divide out the 70, which 50 and 70 have a common factor of 10. Take the natural log of both sides. So k is going to equal the natural log of 5 over 7 divided by 5, and that bottom 5 is coming from there. So I don't know if you guys remember, some of you did and some of you didn't, they do the CSI project in Algebra 2 or Math 3H. This is what that project came from. This is the same formula that you use there. It looked slightly different because it already was in terms of natural logs, but the idea is still the same. If not, if you didn't do that project, no worries. So our formula is going to be 30 plus, I'm going to go back up to here, and instead of putting 80 as the final temperature, I'm just going to call it T, because the point is to give you, to be able to give someone, they give you a time and you can give them a temperature. And because it's cooling, we see that K is negative. Again, you won't have to memorize the Newton's law of cooling for the test. If you are asked to use it, it will be given to you. You'll just have to know how to put all the pieces together and what all the variables represent. Find the temperature of the object after 20 minutes. So T equals 20. We can take that nice little model that we just made and plug in 20. And then this one doesn't even require a logarithm. All it does is requires to plug into our calculator, and we would get 48.329 degrees Celsius, which to me makes sense because the first model was only after 5 minutes, and after 5 minutes it went from 100 to 80, and after 20 minutes it's down to 48, but you have to keep in mind that the temperature of the surrounding room is 30 degrees Celsius. So it's going to cool quickly. Alrighty, when will the temperature of the object be 35 degrees Celsius? So this is when we put 35 here, and we're asked for the T. I wrote 7, but I gave myself some space, so I must have known that's not what I meant to write. So there's 70. Subtract the 30, we get 5 equals 70, e to the negative 0.067 t. Then divide by 70, and 5 over 70 reduces to 1 over 14. Take the natural log of both sides, and we get that t is going to be equal to the natural log of 1 over 14 divided by negative 0.067, which is about, when you plug it into your calculator, 39.389 minutes. So in almost, 40 minutes-ish, it'll be to that. I'll plug that into the calculator for you just so you can see real quick how to make sure you do it properly. So it's the natural log of 1 divided by 14. You got to close out that argument, divided by negative 0.067, and there you go. Alrighty, that's it for 3.5.